This is StarTalk, and I'm your host, Neil deGrasse Tyson, your personal astrophysicist, and I hail from the American Museum of Natural History right here in New York City, where I also serve as the director of the Hayden Planetarium. My first planetarium as a kid when I was 9 years old, and I was never the same since then. I think the universe found me. For this edition of StarTalk, it's the ever-favorite Cosmic Queries, fielding your questions on a pre-solicited topic. And today's topic is the multiverse. I know you've read about it, I know you've heard about it, and I know you're itching to know more. And I've got my co-host, Chuck Nice. Chuck.
Hey, Neil.
You're gonna help me get through this.
That's right. I have the questions right in my very hand.
Solicited from
all over the internet, wherever our fans may be found. Their inquisitive little minds want to know all sorts of things.
And I needed backup for this, because I know a little bit about the multiverse, but I claim no particular expertise in it. So we got on the horn and called one of my old friends and colleagues, Paul Steinhardt. Paul.
Yes. Hi.
Welcome to StarTalk.
Well, thank you. Thank you for having me.
Professor of Physics, Princeton University.
Yes.
And you are a proponent of one of the multiverses that people have been talking about.
Well, I'm not sure I would put it quite that way, but I'm actually a proponent of alternatives to the multiverse.
Oh.
Yeah.
Oh.
Really?
Yeah. Okay. So I'm not a big fan of the multiverse. As
really?
You know.
Oh. Okay.
Why not? What did the multiverse do to you?
The multiverse destroyed one of my favorite ideas.
So
it's a problem.
Okay.
Problem for you.
Problem for me. Yeah.
Okay. So what was your idea that the multiverse destroyed?
Well, it's an idea that we call cosmic inflation. One of the long-standing problems that we've had in trying to understand the universe is why the distribution of matter and energy is so uniform on large scales. And we thought we had a really...
In other words, I look to one side of the universe, there's statistically a number of galaxies and stuff, and any direction I look, it kind of looks like that.
That's right.
And you're saying it shouldn't look like that?
Well, according to our initial idea of the Big Bang, the universe should have emerged from some random quantum state and been had a very uneven distribution of matter and energy, and space itself should have been curved and warped. And all that should have happened is that you just stretched that out over time very, very slowly. So that if you looked at the universe today, you should see remnants of that unevenness and warping.
Like an area where there's tremendous amount of matter and other areas where there's hardly anything, and bizarre curvatures of the space-time continuum.
Yes.
Like a fire.
Yeah.
So a fire is like unpredictable in the way it moves. It has certain burn patterns. And so you would look for that to see where the fire, how it progressed in certain areas. But it wouldn't be like a very uniform...
Okay, I hadn't thought of using fire, but yeah, I guess a room would not burn uniformly, because some things in the room are more flammable than others.
Okay.
So, yeah. That's a good...
Let me tell you something. You have no idea.
I just bailed you out of that.
No, that's exactly what I meant. That's exactly what I meant. But I was just like, the way you looked at me, I was like, you shit the bed again, Chuck.
All right, we're trying to wrap our heads around this. Okay, continue, Paul. Okay.
So we thought that the idea for solving this problem was to have a period of very rapid accelerated expansion that occurs right after the bang. So that instead of expanding at a sort of slow, modest rate that would preserve this unevenness, instead you would stretch it at such a space at such a fast rate that the matter and radiation that existed before would all be spread out, dissipated. All you'd have left is the energy that would be driving this expansion, this super expansion. And then when that energy decayed into ordinary matter and radiation that we see today, because it had made
matter and energy are one and the same. E equals mc squared tells us that.
Yeah, but it also includes light and other forms, all forms of energy. Then you would discover that the only energy that was left was very uniformly distributed. So that was the initial idea. That seemed to be a sweet idea for explaining how you would get this
universe
expansion. Universe we see, which has this peculiar and unexpected uniformity.
Okay.
So then we came up with another added idea to this, which is in this description I just gave you, I didn't include anything about quantum physics. So I said just stretching the universe would make it uniform, but quantum physics resists uniformity. It produces fluctuations, random fluctuations that prevent perfect uniformity. And they would lead to some regions of space ending inflation slightly before or after the average. So you wouldn't end up with a perfectly uniform universe. You'd end up a universe with a specific non-uniformity in the distribution of matter.
That you can predict.
That we thought we could predict. Okay, it seemed to be predictive. It seemed to be something you could work out on the back of an envelope.
That you could work out on the back of it.
That some of us worked out on the back of it.
Me and my supercomputer equals you in the back of your envelope. Okay.
But the and curiously enough, those naive predictions agree with what we've observed when we actually look out in space with the pattern of unevenness that existed in the early universe.
It's not as uneven as it might have otherwise been, but it has the right amount of unevenness that's consistent with the hypotheses.
With this naive calculation.
So what's wrong?
Okay.
What's the problem?
Well, there are a couple of things wrong with this idea, as we've discovered. The first is that it had presumed that after the Big Bang, it would be easy to get this inflation. That just by introducing the right forms of energy, hypothetical energy, into the universe, you could automatically start inflation. And so you could begin with a very random, uneven state and start the inflation.
You would tune inflation to occur when you needed it to match the universe that we know.
Yes, but you also need to start the inflation. It needs to ignite if you somehow.
You can Chuck's analogy to flames, yes.
But we thought it would be easy to ignite. But we discovered actually the opposite is true. So as an analogy, imagine that I was trying to, I told you I had a theory for how to become a billionaire.
Okay, I am very interested.
I thought someone might be.
I'm taking notes.
Okay, so I have a theory of how to become a billionaire, and I show you a little part of my theory, which it tells you how to invest some money, and sure enough, it demonstrates that it could make some money by following that procedure. And so you buy my theory, and I give you the book which explains the theory, and you open up to page 1, and it says, page 1, let's assume that your parents were billionaires.
So basically, this is Trump University. Okay, all right.
How to become a billionaire, start with $1 billion.
Right.
Well, this is essentially what happened in the story of inflation. We thought originally just simply stretching the universe would be an easy start, but we discovered actually only under very rare conditions, essentially the conditions you needed. You needed to start with the universe which was already smooth enough and unwarped enough. Only then could inflation start.
Ooh.
So it's just like saying, I need to have $1 billion in order to become, in order to make $1 billion.
Okay.
So that was the first big problem, and we've never gotten around that up to the present time. We've known about this for 30 years, but we haven't figured out, despite lots of clever attempts, how to get around that problem.
You're all such idiots. You can't.
No, it turns.
I'm telling these early universe guys.
That's so funny.
You've been 30 years now. I'm waiting. All right.
Still waiting.
Yeah. Is it because the problem's hard, or because you all just aren't smart enough?
It's because probably it's actually not a good way of smoothing the universe out.
Okay.
I would say it's probably not a good. It's
answer.
probably not a good book that I gave you for the billionaire solution
Recipe.
Then the second problem that we found is, well, suppose I let you start as a billionaire, okay? I give you the conditions you need to start inflation, okay? But, and I let you choose your inflationary energy to have whatever properties you want. We thought that you could then calculate, as I said, on the back of an envelope what the predictions would be. But there's a little something that we left out of the story that we didn't realize. When we thought about these quantum fluctuations that slightly change the rate at which inflation ends one place to another, inevitably there's also going to be regions which are going to have large quantum fluctuations. They're not going to just delay the end of inflation by a little bit, but by a huge amount. And the longer you delay, because this inflation is stretching the universe so fast, the bigger those regions become. So a typical region is not the region you thought it was, which just had tiny fluctuations. A typical region, in terms of where most of the universe is one of these huge regions which continues to inflate, and then itself, it will repeat the process, patches of it will end inflation, but patches of it will continue. So that
Just within it.
within it.
Yes.
And so it'll keep producing patches and patches and patches, with most of the universe continuing to inflate, and only rare patches where it ends.
And we don't see these patches.
According to this idea, we would live in one of these patches, but these patches are not all the same. This is where the problem begins to break down.
I know, but looking around, we don't see such non-uniformity in the universe.
The only thing, we see uniformity. We don't see any evidence.
Unless our entire universe is one of these patches.
Which is the concept of multiverse.
Now we get it.
Oh.
But
So that's one kind of multiverse.
Right.
But that is one patch of the multiverse.
Right.
And that is, but the problem is that, so if
Wait, just to be clear,
Yeah.
this is not a universe in some other dimension.
Right.
in
No.
another-
This is all one universe.
This is
One
an
universe.
Area.
volume, whatever,
right.
in a meta universe, and we're thinking it's our thing.
right,
That is
we think it's everything.
fascinating.
Right. But outside of that, our patch, if you went far enough out, would be more inflating universe, and finally you'd hit another patch. That patch would have different properties.
Right.
Due to
Quantum
different fluctuations.
Exactly.
Quantum fluctuations would cause different properties in that little patch.
But that means you can actually travel within this universe from one patch to another and then experience slightly different laws of physics.
Too bad. No.
Damn.
Not.
Okay, why not?
And the reason is because the
can't-
space between these patches is growing so fast, it's continuing to inflate, that light, or neither you in a rocket nor light could make up the
Okay,
difference.
so we can't overcome the expanding boundaries between us.
Yes.
Can't beat the expansion.
Right.
You can never get ahead of that expansion.
Right.
So you're never going to reach that patch.
Right.
Okay.
Wow.
So it's completely, it's there in
That's
this
good,
idea.
though, because you don't want to wander into a place that has slightly different laws of physics.
Yeah, for example, where all the molecules in our body would decay into radiation. That wouldn't be
that
a
would
good
be cool.
news.
Yeah.
Or perhaps I show up in the wrong outfit.
That's
And
right.
that
That's
would be disastrous.
Perhaps.
I believe this is black tie, sir. Okay.
So, Paul, how would you ever test this?
Well, it's actually hard to test this idea because one of the consequences of this idea is over time, you produce patches of ever increasing variety, so that every conceivable possibility that can occur will occur in some patch.
So the patch that has a slightly different law of physics will have patches that are slightly different from it.
Yes.
Which will have patches slightly different from it.
Right.
Wow.
So it's a theory which...
Well, you're freaking us out here.
That is freaking crazy, man.
Well, I think it is. Because our goal was to explain why the universe is the way it is, and we haven't
But our heads are exploding, but your head exploded long ago when you
Yes.
first did it. Now you're just cool with it.
That's right.
And what's also like blowing my mind is that, I mean, it's so incredible that you're able to conceptualize this as all a part of, like you say, the meta universe.
One expansion of a thing.
Whereas our common perception of a multiverse is we're making jumps and leaps to these parallel universes that are existing on different planes. You're saying, no, this is like whirlpools in a giant lake.
Yes.
Yeah, that's
Yes.
amazing.
A connected fabric of
pathway.
space.
Right.
Yeah.
Yes. Okay. Yeah. That's.
Wow.
Let's get.
Yeah, let's get into the.
Okay.
Yeah.
See, and we'll still. Well, I guess we're not done with you here.
No, I know.
Wow.
All right, Chuck. What do you have?
Here we go. Of course, we always start our queries with a Patreon patron.
Are these people who paid to get their question first?
Yes, because
Is that even fair?
listen. Life is not fair. Okay?
Fine.
That's all we know. Life is not fair.
These are supporters of the show.
People support the show, and so we support them back by giving them preferential treatment.
Mutual back scratching.
There you go.
All right, go.
It's the same reason why my parents like me better than my siblings.
I'm not even going there.
There you go. Or at least they pretend to. Here we go. Christopher Cohen from Patreon says, hi, Dr. Tyson. How far do you think we are away from determining the theory of everything, i.e. a theory of quantum gravity? What will we need to perform experiments that could prove or disprove a particular hypothesis? Chris and Samantha Cohen from Harworth, New Jersey.
Yeah. So Paul, how interconnected is a theory of everything to what's going on the frontier of multiverse thought?
I think it's intimately connected in the sense that one of the problems we talked about already was how you would start the universe off. So a presumption of this conventional picture is the universe has a beginning.
The only cosmologists get to sound like God. Well, this is how we're going to make the universe this way this time.
Exactly.
And then
Right.
the power that they wield. All right, go on. Yeah.
So the question is how. So the idea is that at some point there was nothing. No space, no time, no matter, no energy.
That's the presumption.
That's the presumption, which we can question. But that's the presumption. Then suddenly it burst into something. Space, time, filled with energy that was first quantum, and then suddenly became later, a few instances later, large enough and became classical, described by general relativity. Now, those are words. What actually happened there? What's the theory that explains that creation event, or that replaces it with a better idea?
Let's go to the tape.
Go to the videotape. That reminds me of, the Sid Harris cartoon where there are two physicists at the chalkboard, and it's filled with equations. And then at the end, in the bottom right-hand corner, it says, then a miracle occurred. Right? So the other physicist says, we need some more detail here for what happens at this stage. Yeah.
That's the theory of everything.
That's the
So that's what we're looking for. Is
okay,
a theory of
so it would
quantum
dovetail
gravity.
into what you're trying to describe what happened after.
Yeah, a full theory would have to incorporate a quantum theory of gravity and an explanation of either this creation from nothing or something that replaces it with a different idea.
So
And
is
we don't
that
know.
where you hear people talk about the eternality of matter? Like that it's not about that it came from someplace, that it just always existed? I mean, I've actually heard that as people that try to explain that's how everything started, and that this just goes over and over again.
Well, so the idea of this creation idea, of this Big Bang, the traditional Big Bang idea, is that there would have been no matter.
Right.
There would have been no space for matter to even exist in. So matter already presumes a notion that it exists in some space background.
Stupid.
I know. What the hell was I thinking? Chuck, you idiot!
But let me say, we don't know that this creation idea is right.
Right.
So there are some of us, and that's
Yourself included.
myself included, who have been
Rethinking the creation scenario.
Yeah, and thinking that maybe what we thought was a Big Bang was really a big bounce. That the universe went through a period of contraction and then bounced to expansion. So that space would not have had a created moment, but would have existed before, during, and after.
That's what I was trying to say.
Yeah, so there's your eternality,
There's your
at least
eternality.
of space.
At least of
Yeah.
space.
And what do you call this idea?
Well, there are different versions of this idea. The Big Bounce is just describing this event.
I like that. Two syllables. Yeah.
A version of it, the universe undergoes not just one bounce, but periodic bounces. So we call that a cyclic universe. So the universe goes through
It
cycles
sounds a
of
little
it.
better. Okay.
If you are into your Greek, one version of that is called an ekpyrotic universe. Another version of it is
Worst name ever.
Thank you.
Ekpyrotic universe. Oh, who wants to live there?
We might.
Rolls off the tongue.
Right, exactly. Oh, by the way, once you get done with the ekpyrotic universe, why don't you make your way over to the enema universe?
Wait, so ekpyrotic for the Greek means what? What are those words?
From out of the fire. So actually an ancient Greek idea was the idea of a universe went under regular periods of creation, evolution, and then cataclysm, disappear, and then a new universe would be created, an ekpyrotic universe.
Okay,
Let's go with Phoenix universe, maybe?
Phoenix is another version
Phoenix.
of this.
Because otherwise you're just showing off that you know Greek and obfuscating what.
Fair enough.
Right.
Imagine if the Big Bang had been called something else.
Yes.
Something with multisyllable
Which
Greek.
it was at first.
Right. Then it would not have caught on.
That's true.
In popular culture and parlance.
Absolutely.
Big Bang, black hole, this kind of thing.
This is true. So marketing's important.
Marketing, very important. We're going to take a quick break.
Okay.
And when we come back to StarTalk Cosmic Queries Edition, we've got Paul Steinhardt, physicist at Princeton University, and he's our expert in-house on the multiverse. See you in a moment. We're back on StarTalk Cosmic Queries Edition. Today's topic, the multiverse. Topic I would not dare tackle on my own, so I brought in Chuck Nice.
Yeah. Of course, Chuck knows everything about the multiverse. Right.
Chuck is reading questions from you, our fan base, and I brought in Paul Steinhardt, Princeton University professor of physics.
And it's been a fascinating conversation thus far.
And he's been doing some thinking of his own on the multiverse. So, so a quick question. Your ekpriotic universe, which is repeating, bouncing, you remove the need for singularity, is that correct?
Yes. So time would exist arbitrarily far back, maybe infinitely far back in time. Maybe space and time existed forever. And we're just in the most recent cycle.
I'm going to ask you a philosophical question. Did you come up with this idea because the singularity was too hard? And so you needed an easier way to understand the universe? Or did you have compelling reasons to go there?
Actually, it's a very practical reason. I didn't have a philosophical outlook at all. It was to get rid of the multiverse problem. Because the multiverse caused the...
you took out a hit on the multiverse. The multiverse got 2 in the back of the head.
That's right.
And then Paul went, leave the gun, take the cannoli.
Damn.
Wow, that's pretty wild.
That was the motivation, though. That actually was the motivation, because the multiverse, essentially, as I was saying at the outset, destroyed an idea which I thought explained how the universe could have been smooth and uniform. Right. Just because we didn't properly understand the effect of quantum physics, and that due to these rare quantum effects, it totally changed the structure that instead of getting a smooth universe we expected to get, we got this patchy universe which every outcome is possible.
So I want to explain it in a sentence that feels comfortable with me.
Good.
This patchwork universe where you have causally separated regions that cannot know about one another, they are nonetheless connected in the fabric of space-time.
Yes.
We cannot and should not think of them as some separate parallel universe in another dimension, as is so commonly thought of in movies and the rest.
Right. Yeah.
Okay.
That is really just
it's mind-blowing.
Incredibly mind-blowing concept.
What other questions you got?
Let's get back to the questions. All right, this one from Greg Fisher on Facebook says, hi, Dr. Tyson et al. I remember reading a while back that in a quantum state, electrons were shown to not only have spin, but were kind of able to jump or teleport between and within their shells. While this still seems a bit far-fetched, and I'm not a physicist, hey, thanks for that, Greg. Thanks for letting us know that you're not a physicist, because I was very concerned. What's new, and what can be explained about this?
So, Paul, this is not specifically multiverse, but if you're worrying about quantum phenomenon, it's got to show up at some point. We know that when electrons jump energy levels, or even when particles, what we call tunnel from one state to another state, the time delay is basically zero. Isn't that correct? A particle can show up in one place having traveled from another place. If it tunneled there, it got there faster than the speed of light. Isn't that correct? Is that the wrong way to think about it?
I think it's the wrong way to think about it. Right. I think there's a period of time during which its location is uncertain. And if you account for that lost time, that's the time it would take that would be longer time than it would take or equal to the time it take light to travel from its first location to the other. So it's like you would see it here, and then there'd be a period, if you weren't watching, that it would suddenly appear here, and then that period of uncertainty would account for the light travel time.
Okay, now the period where you're not watching, that's a necessary...
Or can't see it.
That's a necessary part of this phenomenon.
Yes,
right.
Because to see it would mean you'd have to be shining light on it to see it. Now you'd be cheating. You'd actually be kicking the electron, and you'd say, oh, the reason why it went from here to here is because I kicked
light.
it.
Right.
Yeah, yeah.
Use the light.
So it's important that you don't look, okay? Because then you're not studying the tunneling phenomenon.
Well, that's like the old joke, I know how to teleport. And they say, prove it. And you say, okay, I'm going to go to San Francisco right now. I'm back.
Okay.
You know what I mean?
It works.
It works.
I can't disprove it.
Okay, so you said something fun and deep, as you have been doing in this time that you've been sharing with us, that for a particle to disappear from one place and reappear in another spontaneously via some kind of tunneling phenomenon, it does that because you stopped looking at it. The
Yes.
act of having looked at it, the act of looking at it sort of keeps it in that quantum state, if you will, in this scenario.
Or kicks it out. Or
kicks it. You look at it, it kicks it
you
out.
interact with it. Now you're studying a different effect.
Right, right. And this is happening all the time for everything. It's just that we can be illuminated by light, but our mass is so high that we don't jump to another quantum state, body and soul. But an electron is such low mass, and it has this interaction capacity with a photon that you can't shine a photon on it and expect it to stand there and smile for you.
Yes.
Okay.
Exactly.
Wow. Okay.
Yeah.
That's pretty awesome.
So the act of trying to measure it changes what you're trying to measure.
Right. You can't measure it because once you pull out whatever it is you're measuring, that actually affects it.
Right. And the New Age movement completely misunderstood this, thinking that it's your consciousness that's somehow affecting it, and it's a human thing. No, it's the act. It's the act of measurement is a thing, whether or not the human is doing it. You can have a machine,
Right.
Whatever, it doesn't matter. Right.
And this spontaneous process, by the way, is the same idea that's involved with producing the multiverse. It's a similar tunneling or decay-like process. In this case, it's a decay of inflationary energy into matter and radiation that's occurring randomly due to quantum effects. And the fact that it's random and sometimes produces a huge expansion is all part and parcel of this quantum uncertainty, randomness.
Gotcha.
Quantum is some badass stuff.
Let me tell you, it's crazy. It's a powerful thing. Yeah, and the fact is that I'm going to be very honest. I don't understand any of it.
That's fine.
Okay, I'm just letting you know.
No, but you don't have to. By the way,
I mean, I understand what you're
Paul, who was
saying.
it said? Was it Feynman? So one of the greats of yesteryear said, "The day you say you understand quantum physics is the guarantee that you do not." Because
Probably
it's,
so, yeah.
it's not something to understand. It
Okay.
just is.
Oh, right. Okay. Well, then I feel much better.
No, you just
Okay.
no. We were freaking out. Our historical brethren who discovered this, they were freaking out just like you are right now.
Right.
Yeah.
Oh my God, a particle, a wave? Why? Who? What? Einstein said God does not play dice. People were freaking out, even Einstein. So you in good company, Chuck.
Right,
And even today, there's still a community of people that debate the interpretation of quantum mechanics, and then there's another community of us who just say,
It just is.
This is it.
"Shut up and compute."
Compute, exactly. I'm in that camp, by the way.
me too.
And by the way, if I had a time machine and I somehow found myself in the 1920s, I would be the greatest heralder of the discovery of quantum physics, which I think did not get much public play back in the 1920s when most of the foundations of it were laid to paper. I mean, think about it. Newspapers of the day aren't saying a new branch of physics has just been discovered. It's not there.
Yeah.
It's only when it became useful for the IT revolution and
Right.
our entire the creation, storage, and retrieval of information has anyone been able to fully appreciate what came out of that era.
That's pretty
The
wild.
transistor too. You needed
And partially it's because there was a lot of confusion as to how to interpret the idea and exactly at
What
what
it meant.
point it was what it meant and at what point it was convincingly true.
So the point is, as a professional physicist, you study quantum physics, which historically had only been applied to the small. Now, as a cosmologist, when the entire universe was once small, you're invoking the rules of quantum physics
You have to.
now affect the entire universe.
Right.
Wow.
And the effects.
Now that's pretty
huge.
awesome.
Well, think about it, right? Because when the large
exactly.
were small, quantum physics is kicking cosmic butt,
Okay. And you know
not
what?
just particle butt.
And that's in the Bible. The large shall be small, and the small shall be large. So, yeah, of course.
All right, Chuck, what else
All
you
right.
got?
Hey, this is Matt
was a
Eli
great
from
question.
Facebook. That was a great question that we had. Matt Eli from Facebook and also from San Antonio, Texas. A little more, he wants to know this, a little more existential. Why should we take the multiverse theory seriously in the first place? Might there be extraordinary evidence for this extraordinary claim?
Whoa.
He is not the least bit skeptical.
Good. I like this question.
Yeah, so go ahead.
Yeah, it's you got to admit, Paul, to assert multiple universes is extraordinary. And if you're not on the tail, and you're a theorist, last I checked, so you're not even, well, of course, good theorists think of how to test
Yeah,
their
I think you
hypotheses. Have you? How's that for a setup? Good theorists do this.
Right.
Or do you? Yeah.
Well, I think I've already sort of laid out my cards and said that I think the multiverse is a sign of breakdown of this inflationary idea. It's a failure it's a failure mode of the theory, something we didn't expect. It wasn't designed to produce a multiverse. It's something we discovered after the fact. And the problem is that because it produces an infinite number of patches of every possible variety, if you ask what the theory predicts, the answer is nothing, or everything, or anything.
Gotcha.
So it's a little bit analogous.
If it explains everything, then in fact it explains nothing.
Yes. So in my view, that makes it no longer a scientifically interesting theory. So it's not testable.
Even if it's true, it's just not interesting.
It's not interesting because anything you'd measure, you could say, oh, we live in that patch of the universe. And then you measure something else tomorrow, and it doesn't fit that patch. You say, oh, they must
live
have
in
been
the
that
patch where both of those are the fact.
Yeah, that's right.
Right.
And if it's,
that makes sense. I mean, yeah.
and according to the multiverse idea, if it's physically possible, and obviously our physical world is one of the possibilities, then it must exist somewhere
Unless
in the multiverse.
we're a simulation.
Ooh, no,
But even that would be part of the multiverse.
There's the.
You can't get away
Oh
from this
man,
bad idea.
drats.
Once you have a bad idea, you can't get away from it.
That's funny.
Drats.
All right, so there you have it. Okay. Hey, Matt, nice question.
Wait, so you agree that it doesn't really set the standard yet for a testable theory?
I think by construction, it does not. And if you read what the proponents of the multiverse say, that's exactly what they'll tell you. So it's
What about the quantum foam bursting forth multiple whole other universes from the very early universe? And these would be universes that you would be able to see in a higher dimension, but they don't interact and they're perfectly
so
happy.
they're separate fabrics.
Separate fabrics, yeah.
I don't know what to make of that. That's another untestable idea in principle. So it's another version of so there are two possibilities. One possibility is that those different fabric regions have completely different properties, again, like the multiverse, and it's just random chance.
Like the patchwork multiverse.
Like a patchwork multiverse in which you wouldn't, in which again everything that could happen will happen, in which case it has no scientific predictive value. Or it could be that you have a theory which says actually the same thing will happen each time, every time you produce one of these fabrics, so that if I suddenly transported to the other one, imagine doing that, it would look familiar to me. That's a different story. That's a predictive theory.
Yeah, that is, right.
Yeah.
But the problem is you can't get there, is what you're saying.
Yeah, and so it doesn't have a meaningful scientific value.
Right.
It's just a
Paul,
concept.
isn't it true, for reasons that I never learned because I never took advanced field theory in graduate school, but my wife did, and she has a PhD in mathematical physics.
I know your wife, and she's smarter than you.
That's right.
I'm just saying.
But from what I've been told, gravity is not contained in the space-time in which it is formed, in which you have it. So in other words, the effect of gravity can leak out of whatever is the membrane that it's contained and be felt by other universes outside of that? Unlike electromagnetic radiation, which is trapped within the space-time, gravity is not. I've heard that.
So I think you're referring to theories like in string theory, you have extra dimensions, and where we might live in a membrane-like surface, in which we think we're living in a world of three space dimensions. There's actually extra dimensions, which our particles can't move there. Yeah. Our light can't move there, so electromagnetic radiation can't move there. But gravity would be felt even along that extra dimension. So that, for example, if there were another similar membrane parallel to us. Now we are thinking about this idea of parallel universes.
This is the parallel.
And something were happening over there. Let's say a matter lumped together to form a star, or a black hole, or something like that. That would be felt. Its gravitational effect.
So why isn't that dark matter? In our
Could
universe.
be.
Dark matter in our universe would be ordinary matter in a parallel universe that's leaking into ours, and we're mysteriously inventing stuff to account for it, when in fact it's just ordinary matter.
I think that's a conceivable idea that it could be matter on the other side, another membrane that's a small distance away. It couldn't be like our matter, because if it were, it would also, when it gravitationally clumped, it would produce radiation, and that radiation would affect us as well in a way that we know there aren't those sources of radiation there. And the dark matter, one of the things about dark matter compared to ordinary matter is ordinary matter collapses to form stars.
Can stick together.
And stick together and sits in a halo of very diffuse dark matter. If this dark matter were like us but on the other side, it would also collapse and it wouldn't form the halo, which we know of dark matter that we observe, that we infer from measurements.
And there's another little fact here. Gravity drops off as 1 over distance squared, but if you're feeling gravity from another universe, that's gravity permeating through another dimension,
Yes.
and then therefore gravity from another universe would have to drop off faster than 1 over r squared.
Yeah.
Okay,
But
now-
ever so little, but ever so little.
As of course the foremost authority on this in the room, let me just say, what the hell are you talking about?
It's time for commercial break.
You lost me until 1 over r, the gravity thing there.
If you're spilling out and you got to go through another dimension for it to be felt,
Right.
then your equations have to somehow recognize that fact.
I got you.
The dilution of gravity as you get. So in other words, gravity, the surface area of a sphere, as it grows, you're thinning out whatever the fabric was by the square of the distance. So,
I got you.
A sphere that's 3 times bigger
So because the sphere is expanding.
has
is that
9
the deal?
times the area,
Okay.
and so so it's thin. Whatever was there before is now 1/9 as thin. So gravity thins out at that rate.
Okay, I got you.
But if
Now
add-
that makes sense.
If gravity, if you're going to thin gravity
I'm
out,
thinking of this as a blowing up balloon.
okay, if you want to thin gravity out into a whole other dimension,
Right.
then that equation can't just be 1 over r squared.
Gotcha. Now that makes sense.
Let me just get, Paul, was I okay with that explanation?
that's
okay.
fine.
All right.
I get
Yes.
the
And for those of you listening at home, you're welcome.
When StarTalk comes back, more on the anatomy of the multiverse. We're back on StarTalk, and I'm here with Chuck Nice.
Sir.
And an old friend and colleague of mine from my Princeton days, Paul Steinhardt, professor of physics.
And Lord of the Phoenix Universe.
So Paul, does your chair have an endowed name to it?
It does.
What is that?
It's called the Albert Einstein Professorship in Science.
Excuse the hell out of me.
That's pretty rough, man.
Okay, I'm
That's-
thinking it was some name, some rich guy that just gave money.
No, the Albert Einstein
Okay,
professorship.
so do you realize you could only be a disappointment?
Yes, absolutely. That's the price.
Oh man, that's just so wrong. That's so,
I know. I just
wrong.
thought of that in that moment. I'm sorry.
that's funny.
So Chuck, we're Cosmic Queries. What else you have?
Yes,
Go
let's
for it.
move on.
Multiverse Cosmic Queries.
Multiverse, we are talking about. This is somewhat in that range, but Michael Ranger from Twitter says this: reality is granular. I love how people put their own little stuff.
The thing. Let them do it. Let them do it.
How then can, say, the Earth's gravity reach infinitely far? Wouldn't it eventually wink out?
Ooh. So let me recast that question.
Yeah, it's a good question.
If in a quantum construct of the universe, you cannot get arbitrarily small things. You cannot have arbitrarily short time intervals because there's a quantum size that limits it. Do we agree? Mm-hmm. Okay. So if you have gravity dropping off ever so slowly, 1 over r squared, and that means r gets bigger and bigger, gravity gets smaller and smaller, but there's always something there. You can always calculate how much is there. Is there some calculation where the gravity is so low, it goes from some quantum higher level to zero? Did I say that? Did I make sense in that question? Was that a fair interpretation?
No, that's a
of the
fair
man's question?
interpretation.
Okay.
I wasn't sure if you were talking about time or space, though. You're talking
Talk
about
about just gravity.
just gravity as we go out away
strength
from the
of gravity.
source.
Right.
You
As
go
it moves
away.
away from
Yeah.
Earth. So it's Earth's gravity.
Right.
in particular.
You know, it's it's like cleaning up broken glass. There's like a gazillion pieces that you'll never get it all, but eventually there's the last piece of glass you've cleaned, and there's no more glass left, even though it felt infinite at the time. So, is there a last piece of gravity that Earth is expressing into the universe?
The various. I'll give you one interpretation of that question. Let me see if that will help answer it. So, it's important to appreciate that the Earth hasn't always existed. It came into existence. So before it came into existence, there was no gravitational field associated with it. Okay, there was matter that was going to eventually come together to form the Earth. So if you go far enough out, so that if you go far enough out in space, you would not know that the Earth was about to form.
Ooh.
Then the Earth.
Wait. We got to wrap my head around that. So Earth is about 4.5 billion years old.
Yes.
If you go 4.5 billion light years away, there's a point where Earth had not yet assembled from the void.
Yes. If you were looking
Even
from that
have a
vantage point.
field of gravity
Holy
to measure.
Man. Okay. I'm telling you right now, there are people listening to this and they're just like, I am never doing drugs again. This is so crazy. I'm never doing drugs again.
So you're out there.
They're just going to do cosmology.
Yeah, exactly.
Right.
You don't need drugs when you got this. You really don't. I mean, that's freaking crazy.
Take up cosmology.
Just take up cosmology, people. I'm telling you right now.
So what you're saying is you could be there and you would watch the formation of a source of gravity in front of you. Even though it's too far away to see, you would you'd measure this gravity arise.
Yes. So it'd be like throwing a rock in a puddle, and eventually the wave is going to meet you, is going to reach out to you, and then you'd be aware that a rock, if you weren't using your eyes, you're just feeling the water, you'd be aware that something happened.
Except the rock hitting the puddle was a spontaneous thing.
Yes.
The assembly of the Earth was slower and piecemeal.
That's right.
Okay. Okay, so that's an awesome reply, but I think it still avoids the question.
Yes.
Is there a point where the gravity of something the strength of gravity of something quantum drops to zero from some quantum level above it? When I say quantum, I don't even mean quantum physics so much as can it smoothly go to zero asymptotically or not? That's really the question. You could say I don't know.
Yeah, I was going to say that.
Even though you're a Princeton professor, you could say I don't know.
Well, the question could mean, I'm more confused because the question could mean various things. So let me mention another issue, which is there in the...
By the way, let me just say, I am glad that right now you guys are not two surgeons trying to figure out how we should approach this open heart situation.
What is that wiggly thing? Should we take it out or leave it in? Let's
Go ahead.
Scissor, paper, stone and find out.
Right, scissor, paper, stone. So go ahead. Sorry.
I was going to say there is a deep puzzle, which is if you buy this idea that the universe began from a quantum beginning, which rather than a bounce, one of the puzzles there is how do you go from a quantum world to a world which is described by your 1 over r squared force and by the laws of general relativity? How do we go from quantum to classical? And at this point, what proponents do is simply wave their hands and said, something must do it. And so we'll just, sometimes we work on one side of this something, sometimes on the other. But exactly how that occurred is a mystery and is another reason to be suspicious of this setup of a Big Bang leading to a classical expansion.
Okay. All right.
All right, we'll give you another question here.
Here we go. Here we go. I'm going to say, I'm sorry. I lost his name. I wanted to answer him. Michael, here's the deal. We didn't answer your question at all. So,
No. Here's what I say. We turned it into a better question that we
actually,
could answer.
that's what really happened. We turned your question into a better question.
Or a question, just a question we could answer.
Right, there you go. All right. Here we go. Maria Simon from Facebook would like to know, Dr. Tyson, would our perception of time be the same throughout the multiverse? Thanks. I can't wait to see you live on Monday. Where are you going on Monday?
I have no idea where this child is. Oh, no, actually, this show is being recorded. Next week, I'm in the Pacific Northwest.
Okay.
Doing some public talks.
All right, there you go.
It may be one of
your
It could be Eugene,
talks.
Oregon, or Seattle.
Okay.
So, I'm sorry, what was the question?
So she's talking about the perception of time.
Oh, yeah.
And is that going to be, going to be consistent?
So, Paul, we know from relativity that the passage of time is relative to an observer.
Yes.
So, other than that, which we live with, in fact, daily, you realize the GPS satellites at their elevation above Earth experience a different strength of Earth's gravity than we do here. And Einstein's general theory of relativity prescribes the difference in the rate at which its clocks tick compared with ours. And so what that means is when it is telling us what time it is, we have pre-corrected the change in its time because of Einstein's general theory of relativity, so that we all have the same time here on Earth's surface.
Gotcha.
The same time as one another.
No, that makes sense.
It's general relativity at work.
Right.
At work. Okay, so Paul, we got this.
Yes.
But if you go to another one of your multiverse pockets, could just time have a whole other kind of thing going on about it?
Well, certainly there would be no way to synchronize it compared to our time. So, for example, patches would be born at different times. So the period, the time that would have transpired since the creation of our patch to reach a point where there's Earth and people would be different maybe in this other patch. It might have just been born. So
their calendar would be BP for before patch.
Yes.
Okay. All right. So go on. Yeah. Mm-hmm.
Yeah. So it'd be simply no way to correlate our time. So unlike the case of the satellite, where we can send signals back and forth to the Earth to synchronize and to make this correction, and only by having that communication, because we can't communicate with one another, there's no meaningful way to synchronize our
But in
clocks.
the quantum fluctuations of these patches, could time mean something different there? Could a quantum fluctuation change what time is?
Conceivably, it's not part of the usual multiverse picture.
Okay.
It's rather conventional in that sense, that the patches would more or less have normal space and time like we think about here. Although some of them could be, in some cases, the space-time could be so warped that time could never lose its quantumness. It might remain quantum and have a sort of no classical meaning in some patches. That's conceivable, and that's a kind of version of what you're asking.
I like that. So time would just not be even not even a thing.
Right. It may not even be.
Yeah. Right.
Right.
It's just they could figure out some other way to meet you at the corner.
They put it in a bottle.
They couldn't meet you at the corner because space wouldn't have a meaning either.
Oh,
so the corner wouldn't
be there either.
Yeah.
Right.
We got time just for a quick lightning round.
Okay, let's do it.
All right.
Here we go.
Soundbite answers. Okay.
Jonathan Nagy from Twitter wants to know this: will quantum gravity mean GR is incorrect since QFT is based on flat space-time and GR is a curvature? He's just showing off.
Just showing up. Okay, Paul, what's the answer?
Yes.
Yes. Okay. Next question.
Gabriel from Twitter wants to know this: what, if anything, is stopping gravity waves from traveling faster than the speed of light?
Ooh, yeah, Paul.
That's a good idea.
Yeah.
Relativity.
Okay, good.
Dang, you are really good at this part, Paul. I got to tell you.
Okay. We got to take it as an answer because this is the lightning round.
Right.
So,
Not a good answer, but just an answer.
By the way, Gabriel, look it up. Okay, here we go.
Wait, in other words, relativity does not allow anything to go faster than light.
That's
Therefore,
right.
gravity waves are not traveling faster than light.
Correct.
Even though they be gravity and not light.
That's right.
Okay, good.
There you
got
go.
it. Good.
All right. Datons, at Datons on Twitter says this: can a telescope be made to see so far that it sees the Big Bang? What is the limit of telescopes, including the ones that we launch into space?
Because light takes time to move from one location to another, it means as you look out in space, you see things not as they are, but as they once were.
Right.
And as you just take that far enough back, yes, in principle, you can see the birth of the universe, provided that there is matter out there that is as old as the universe. Okay, so now, the reason why we have any evidence of the Big Bang at all is because we have this expanding horizon that is washing over parts of the whole universe that was born 13.8 billion years ago. Here's what would scare the daylights out of me.
Go ahead.
If all of a sudden the cosmic microwave background began to disappear. It would mean that our cosmic horizon would be entering a region of our universe where there is no longer any matter. We'd reach the physical edge of our universe.
And then that wave is coming our way.
No, then there would be no cosmology because we would have no information about what happened in the past. That's why we can see the Big Bang at all.
Okay.
Yeah. You okay with that, Paul? Uh-oh.
Okay. It's lightning round.
Lightning round.
Answer is yeah. That's the answer.
Well, our microwave background is disappearing, right? If it's being redshifted away due to the expansion of the universe. So in fact, it is fading from view. But that's not because we've reached the edge. It's because over time, that's going to happen just because the universe is continuing to expand.
Yes. So because of the expanding universe, we are diluting the evidence of the Big Bang that is coming to us from the part of the universe that we are seeing being born right now. Yes. However, if that is not fading simply at the rate of the universe expansion, but if it's fading at some faster rate than that, that could be evidence that we are running out of matter in the universe for our horizon to engulf.
No.
All right, well, Paul, meet me outside. All right, we are way over time here. You've been listening and possibly watching StarTalk, the Cosmic Queries edition on the multiverse. Let me thank my friend and colleague Paul Steinhardt from Princeton University. Chuck Nice.
Yes.
I think
Got my name there, huh?
I was thinking of Chuck Norris. Chuck Nice.
That's a common confusion.
All right. You've been listening to StarTalk, possibly even watching it. I've been your personal guide through this universe. My name is Neil Tyson, and as always, I bid you to keep looking up. This is StarTalk.